Hello everyone, my name is AdetayoL, a front-end engineer at AdetayoL Network. Today I'm going to walk you through this Akarang advanced problem named Starfleet. So let's go through the problem. In a galaxy far away, there is a constant battle between the Republic and the Droid Army. The Droid Army decided to launch their final attack on the Republic. They have space fighters. Initially, the height fighter is located at Xi and Yi. All of the space fighters move with constant velocity in the positive x direction. That is, at Xi and Yi, a fighter moves to Xi plus the velocity Yi. Let me take that again. A fighter moves a fighter that is at Xi and Yi in the matrix moves to Xi plus velocity Yi in 1 second. The height space fighter broadcasts enemy information at a frequency Fi. The Republic is not scared of the artificially intelligent droid force as they have Yoda. Yoda has a special power. At any time t, he can choose a region of the droid army and block one specific frequency f. This power has one constraint: it can only be applied in the form of a two-sided unbounded axis parallel rectangular box open towards the both opens towards both the directions across the x-axis. There's an image here for clarity. If a frequency f is blocked, all the space fighters in the region have the frequency having the frequency f can't communicate. So given the initial position of the space fighters and their velocity, you are to answer queries of the following term. So one is y up, y down, and t, where y up, which is now represented as yu, and y down, which is also represented as yd, are the bounds on the y-axis inside which Yoda can block a frequency at a time t. In the region described by the query, after a time t start after a time t seconds from the in the region described by the query, after a time t seconds from the start, if Yoda can choose one frequency he wishes to, what is the maximum number of communications he can block? So our input format is, for each test case, is described as follows. The first line contains three space separated integers n, the numbers of the space fighters, q, the number of queries you have to answer, and v, the velocity of the fighter separated by a single space. N lines follow, each containing three space separated integers xi, yi, and fi, denoting the x coordinate, y coordinate, and the frequency at which the height ship broadcasts respectively. Each of the next q lines contain three space separated integers representing yu, yd, and t respectively. So some of the constraints that are given to us are this constraint here, and what our sample input will look like is what we have here, and the expected output is what we have here. So now then we just need to take a step back to know what category of problem this is. First of all, this is dynamic. This falls in the realm of dynamic programming. you see this as we have to divide this all of this into sub problems to solve it. So what things are we going to do that will help us find the solution according to what our question says? Like it says, if Yoda can choose one frequency f it wishes to, what is the maximum number of combinations it can block? So one of the things one of the ways we'll solve it is we'll use range queries, which involves finding specific information within a certain range of values. In this use case, the range is defined by the y up and the y down, which is represented by yu and yd, coordinates of the queries. So another thing we'll do is like all the queries are known beforehand, so this allows for preprocessing data to answer the queries efficiently later. This problem also involves discrete y coordinates, which are compressed and sorted to enable binary search and range-based calculation. So what we'll first do now is we divide the problem into smaller problems. So first we group data, which are the shapes, separately to simplify the query problem. Then we sort the shapes by y coordinates within each frequency group, ensuring the prefix, sums, and binary search can be applied efficiently. When we approach prefix sums, this allows for O1 range and O1 range query results after O of n preprocessing. So this is crucial in terms of fast computation of shapes within that range. Then we use binary search to quickly locate indices corresponding to y down and y up in the sorted y coordinates for each frequency group. So now let's start tackling this. So as said before, so let me expand this so we get a better view of what we need to do. So like I said, we're going to first start with organizing the shape data. This will be done by grouping the shape based on frequency and counting how many shapes exist at each y coordinate. So frequencies. So this map is created to store the frequencies of the shapes, which will be grouped by their fleet. Then the next thing we'll do is we want to iterate through that shape, iterate through the shapes to get each shape in the y coordinates and the shape's fleet. So here we get we'll check now. Want to check if the fleet is already exists in the map. So if it does, we'll just retrieve the corresponding counts. But if it does not, we would create a new map. Now we want to get the coordinates in the ship fleet. So ship F is ship fleet. So just to add a little bit of comments so you could understand a bit. So ship Y. So we'll check if we have the ship coordinates available within the fleet. If we are going to increment by 1, and if we don't, we are going to default it to 0. So now what we're going to do now is we're going to update the 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 frequency map with the modify y counts, that's the coordinate count for each ship fleet. So this brings us to our next step, which is sorting and calculating the prefix sums. For each of the frequency group, we are going to sort the y coordinates and calculate the prefix sums. So what the prefix sums just allows us to do is quickly calculate the total number of ships within a range of y coordinates. This will be done by calculating the count at each y coordinate, so that later we can calculate the total number of ships between any two y coordinates efficiently. So for sorting, we sort the y coordinates for each frequency group to prepare for a binary search. So first thing we'll do is create an empty array. So now we're going to iterate over each fleet and its corresponding y counts map in the frequencies. So now what we'll do now is we want to sort them by the y coordinate in an ascending order. Y1, Y2, the R function. So this will allow us sort it in ascending order. So what we'll do now is we compute a cumulative sum of counts along the sorted y coordinates and update each count including the previous y coordinate. So coordinates equals to 1 I lower than sorted counts. A mistake here. We add the sorted counts. Comment. Alright, once this is done, I think I did something wrong here. Okay, this is problem. So now what we're going to do now is we're going to update the array by doing sorted counts dot length So what this basically lets us do now is it lets us add an entry for the fleet to the sorted fleet count. The first value is the maximum cumulative count, and the second value is the process array of y coordinates and the cumulative counts so far. Then now go to our next step where we need to sort frequencies by the max count, maximum ship count in descending order. So this from here will take us to the next step where we will use binary search to find the indices for the y coordinate range. Max 1 and the maximum value to our sort in descending order. So now it's time to now we have to start processing the queries. We do that to handle each query to find the maximum number of ships within the specified range of y coordinates. So we're going to use the binary search to quickly find indices of y up and y down in sorted y coordinates. Then we're going to using the prefix sum array that we created, we're going to calculate number of ships within that range. So if the maximum count for the currency frequency is already smaller than the best results, we stop checking further. So if we have a good result, we can exit early instead of um, continuous calculations. So what we want to do is we want to return queries map. So map out y up and the y down. So which is the yd and the yu that we were given also. So that's just to take note of that. So let's first set a max count to 0. So then, what we want to do now is want to iterate over the fleet's data, that's the sorted fleet count, and we get the current max, which is the maximum cumulative count for the fleet, and the y count, which is the array of the y coordinates and cumulative count pairs for the fleet. That's what I want to get from the sorted fleet counts. So first thing what we want to do, we want to do a check if the current max, which is the maximum cumulative count for the fleet, is lower than the max count, which at this point is 0, we just break. And if not, we start to use the binary search to check for their indexes. So this brings us to where we have to create a function for the binary. So this is the down index. So now let's create the upper function here. Just use function. So what our binary search does here is it takes in these parameters, which are the counter, the y coordinates. So we have the counts here. So those are the counts. Then we have the y up or down. So which based on the index, down index or up index. That is where we would have whether we're using the y up to search for the indices or the y down to search for the indices. So we also set a low index, which for now is set to 0, and we can so what this function is going to do is it helps us. We're going to find the position of y coordinate in the sorted array counter. In the array counter, the counter which is the array of y coordinate and cumulative count pairs. So when it initializes the search range, it starts low at the start of the range and sets to index. Sure. Okay, let me pick that again. We want to initialize the search range. So on the low end, take the low index. If it's greater or equals to 0, using a ternary operator, we return low index provided along with the function, or we just return 0. Then on the I, we just use the counter length minus 1. So while using while low is lower than high, we calculate the middle index of the current range using, we are going to use mat.ceil method to handle the case where low plus I is odd, ensuring integer division rounds. So what it will later do is it's going to compare the y coordinate at the middle index with the target y. If it is less than y, it moves the lower pointer to exclude the lower half. Otherwise, if it moves the higher pointer to exclude the upper half. So let's get on and do that. Now we're trying to get the mid index. And so as I said, we are trying to check. So then next we're going to return the low the low index where y will fit into any sorted array counter. So if y exists in this array, this will point to the first position y. If it does not exist, this will indicate where y could be inserted. So now let's go back up and continue and finish up what we have here. So as you can see here now, for down index, it takes in the counter and the y position, coordinate position. Then also for the y up index, it takes in the y count and the y up position coordinates. Then also it takes in the result of the down index as an extra parameter, which is going to be the low index in the binary search. Next, we check if the y coordinate at the up index matches the y up or up index exitive. So you want to check if the y coordinates at the up index, if it matches up with the y up or it exceeds the valid range that is required. So that way y count index from the result from the function, if it's not undefined and the position is not does not exceed the valid range, or the up index is so if this is true, then we decrement it. So next we want to check the down count. So I want to check the count going to y down. I want to check the count going to y up. If when we check the down index on the y coordinates counter and it is undefined, we set it to 0, but if it's not, we set it to the count of where the ship fleet on the y down index is. We also do this for the up count. Now we want to get the count. This subtracts the down count from the up count, and what it does is it calculates the number of sheep within the y up range and write down range. We'll get to a max. Now we want to get the max count. So we'll take the max count that we had from before, which is 0, and we'll update with the current value. We'll correct with the current value and count for the current fleet. So all we want to do is we are updating the max count to the maximum of the current value, and the count, so what it does is it updates the mouse count to the maximum of the current value and the count for the current fleet. Then here we return max count. So that's all we have to do for now. Then we run code to test it to see. So let's take a look at what. So I must have done something wrong somewhere. This should be 1. So let's run that again. So now let's submit to see if so it has been a success. So the final thing I would say is this can other approaches that I've looked at that can be used are 2D range queries, which is finding values in a submatrix or range in a grid, or Mo's algorithm, a specific offline query technique for range queries on an array. If any questions and there are any other suggestions, they should be left in the comments. Thank you for your time.